Welcome once again to the Sleepy Science Vault. If you are here, you have found your way back, or perhaps for the very first time, to a place that exists entirely for this moment, for the specific, private, irreplaceable moment when the day is over, when the effort is finished, when the body has finally arrived at the place it has been carrying you toward all along. Rest, true rest, the kind that begins even before sleep, in the quiet settling of things. So let's start there, right here, with you exactly as you are. Feel the surface beneath you, all of it, the blanket or the sheets, the pillow under your head, the mattress or cushion taking the full weight of your body. Really feel it, not with any particular focus or effort, but with the soft attention of a mind that is beginning to let go of the day. The surface holds you. It has been holding you through every night of your life without ever requiring anything in return. And it is holding you now, completely and without complaint. Let your shoulders soften. Let them drop just slightly, not dramatically, not with conscious exertion, but with a small permission, a quiet allowance. You have been carrying something in your shoulders all day, the way most of us do without noticing, the faint tension of attention, the held readiness of a body that has been navigating a world. That readiness can be set aside now. It will still be there in the morning if you need it. Tonight, it can rest. Let your jaw unclench if it is clenched. Let your hands open if they are curled. Let the muscles around your eyes soften. The tiny muscles around your mouth, the long muscles of your back and your legs and your feet. Let all of it gradually, without hurry, without performance, begin to release. Notice your breathing slow, not because you are controlling it, not because you are practicing anything. Just notice that as you settle, as you give your body permission, the breath begins to find its own gentler rhythm, longer, quieter, the kind of breathing that belongs to rest, not to doing. Your body knows this rhythm by heart. It has known it since you were very small. It will find it on its own, given just the smallest invitation. You are allowed to be here. You are allowed to rest. You have done enough today, whatever today held. Enough thinking, enough deciding, enough moving through the world. Whatever is unfinished will be there tomorrow, intact, waiting. It doesn't require your attention between now and morning. It can be set down, here, quietly, at the edge of sleep. There is nowhere else you need to be. There is nothing else you need to do. Tonight, we are going somewhere that is both right outside the door of your imagination and entirely beyond the reach of most human experience. Somewhere that covers more than 2/3 of the surface of this planet, that has existed for nearly as long as the planet itself, and that remains, despite everything we have learned, despite every expedition and every instrument and every depth-sounding survey, in every trawl and every submersible dive. Largely, profoundly, beautifully unknown. We are going to the ocean, and specifically, we are going to the parts of the ocean that science cannot yet explain. The mysteries, the things that researchers have studied and puzzled over for decades, sometimes for centuries, and that still have no satisfying answer. The places where the ocean holds its silence and keeps its secrets, and quietly, patiently refuses to be fully understood. This is not a list of facts. This is not a rapid tour. We are going to take our time. We are going to move through these mysteries, the way water moves through a deep cavern, slowly, feeling our way, drawn forward by the shape of the space itself, rather than by any urgency of our own. We are going to stay with each mystery long enough to truly feel the weight of it, the beauty of it, the particular quality of wonder that comes from standing at the edge of the unknown and looking in. Let your eyes close if they haven't. Let the room fall away gently. The ocean is waiting. There is a question about the ocean that has followed mariners and scientists for centuries, and that still has not been answered to anyone's full satisfaction. How does it begin? Not the ocean as it is now, vast and salt and ancient, but the water itself. Where did the water come from? How did a rocky planet, formed from the same cloud of dust and gas as the rest of the solar system, end up covered in liquid water to the depth of kilometers? How did this world become the blue world, the water world, the world whose most distinguishing feature from space is the extraordinary, planet-dominating presence of ocean? The question is not as simple as it sounds. The solar system formed from a disk of material around the young sun, and the region where Earth accreted was inside what astronomers call the frost line, the distance from the sun beyond which water can exist as ice. Inside the frost line, the temperatures during planetary formation were high enough that water should have evaporated away, leaving the inner rocky planets relatively dry. And yet, here we are, covered in water. The conventional explanation has long been that Earth's water arrived from outside the frost line, delivered by asteroids and comets, the rocky and icy debris of the outer solar system, during a period of intense bombardment in the early history of the solar system, when the orbits of the outer planets were less stable and rocky material rained onto the inner planets in enormous quantities. Comets, with their icy nuclei, were an early candidate. The ratio of hydrogen isotopes in ocean water, specifically the ratio of ordinary hydrogen to deuterium, which is heavier, was used as a kind of chemical fingerprint to compare Earth's water to comet water, and the comparison showed that most known comets have a different isotopic ratio than Earth's ocean. Their water is chemically distinct. They don't seem to be the source. Asteroids, specifically a class of carbon-rich asteroids called carbonaceous chondrites, are a better match. Their isotopic signature is much closer to Earth's water, and there are models of solar system dynamics that suggest the gravitational influence of the giant outer planets, particularly Jupiter, could have deflected large numbers of these asteroids inward, delivering water to the forming Earth over millions of years. But this explanation has its own difficulties. The delivery would have needed to be extraordinarily efficient to account for all the water we have. The timing of delivery relative to the formation of Earth's surface is not fully worked out, and there are complicating factors, including the possibility that Earth may have retained some water from its own formation, locked in hydrated minerals in the accreting rock and released over time by volcanic activity. That make the story messier and more uncertain than it appears on first telling. We genuinely do not know, with confidence, where the ocean came from. We have hypotheses. We have isotopic evidence that constrains some of those hypotheses. We have models of solar system dynamics that make some scenarios more plausible than others. But the definitive answer, the complete, confirmed, mechanism by mechanism account of how the water got here, that does not yet exist. Think about that for a quiet moment. The ocean covers 71% of the surface of the planet you live on. It is one of the most fundamental features of the world. It is the reason the world is habitable, the reason life began, the reason the atmosphere is the way it is. And we do not know with certainty where it came from. We do not know the origin story of the ocean. That mystery has a particular quality to it, a depth that matches the depth of the ocean itself, because it is not a mystery about something distant and abstract, not a question about far galaxies or dark matter or the first moments of the universe. It is a question about the thing that covers most of the surface of our home, the thing that has been here for 4 billion years, give or take, shaping everything about the way life evolved, in the way the climate runs, in the way the continents have been arranged and rearranged across geological time. The ocean is here. It has always been here in our experience of the world, and we don't know how it arrived. That is one of the most quietly beautiful mysteries in all of science. It has the scale of something cosmological, because it is cosmological, a question about how our solar system and our planet were assembled, and the intimacy of something personal, because the ocean is not abstract. The ocean is the horizon at the edge of every beach you have ever stood on, the sound that fills the air at the coast, the salt that dries on your skin after you swim, something completely familiar and entirely unexplained at its origin. Let that double quality settle in you for a while, the familiar and the mysterious, existing in the same thing. The ocean has a heartbeat, not a literal one, not a single pulsing center, the way your heart is a single center, sending blood outward in rhythmic waves, but something that functions in the body of the planet in a way that is analogous to a heartbeat, something that circulates, something that distributes heat and chemistry and life across the entirety of the ocean basin, connecting the poles to the tropics, the surface to the deep, the Atlantic to the Pacific, in a single, slow, planet-spanning flow. It is called the thermohaline circulation, the global ocean conveyor belt, the meridional overturning circulation. Different names for the same slow, vast, incompletely understood movement of water through the world's oceans, driven by differences in temperature and salinity that affect the density of seawater. Thermo for temperature, haline for salt. The basic principle is elegant. Cold water is denser than warm water. Salty water is denser than fresh water. In certain parts of the ocean, particularly in the North Atlantic and around Antarctica, conditions combine to make the surface water dense enough to sink, dense enough to descend from the surface all the way to the ocean floor, setting the entire column of water above into slow motion, like the plunging of a piston in an engine the size of the planet. In the North Atlantic, warm tropical water, carried northward by the Gulf Stream, releases its heat to the atmosphere, warming Western Europe in the process, keeping places like Ireland and Norway significantly warmer than they would otherwise be at their latitudes. And as it releases heat, it cools. And as it cools, it becomes denser. And eventually, off the coasts of Greenland and Iceland, and in the Labrador Sea, this cooled, salty, dense water sinks, plunges downward, begins a journey along the ocean floor that will take it eventually to every basin in the world's ocean. The journey takes approximately 1,000 years from the surface to the deep Atlantic, to the Indian Ocean, to the Pacific, and back 1,000 years. The water currently completing a circuit that began in the North Atlantic is water that was last at the surface during the early centuries of the second millennium, when the first European settlers were establishing themselves in Iceland, when the Song dynasty was at its height in China, when Notre Dame Cathedral was being planned and begun in Paris. That water has been circulating in the deep, cold dark of the ocean floor for all of that human history, and it is only now, after 1,000 years, returning. The thermohaline circulation is one of the most important physical systems on Earth. It distributes heat from the equator toward the poles, preventing the tropics from becoming even hotter and the poles from becoming even colder than they are. It transports oxygen from the oxygenated surface waters down into the deep, making the deep ocean habitable for organisms that need dissolved oxygen. It transports nutrients from the deep upward to the surface in regions of upwelling, fueling the blooms of phytoplankton that are the base of the ocean food web, and one of the primary mechanisms by which the ocean draws carbon dioxide from the atmosphere. If it slows, if the circulation weakens significantly, the consequences for global climate could be profound. And here is where the mystery deepens and becomes one of the most pressing scientific questions of our time. The thermohaline circulation is driven by the density of seawater, and density is affected by freshwater input. When freshwater, lighter, less dense than salt water, enters the ocean in large quantities, it can dilute the surface water in the North Atlantic, reducing its density, reducing its tendency to sink, and potentially weakening or interrupting the sinking that drives the circulation. Freshwater is entering the North Atlantic in large quantities. The Greenland ice sheet is melting. Arctic sea ice is melting. The rivers of the Arctic are delivering more fresh water to the ocean as the permafrost thaws. All of this is happening at a rate that is difficult to predict with precision, and the consequences for the circulation are uncertain. Some models suggest the circulation could weaken significantly within this century. Some suggest it could reach a tipping point, a threshold beyond which it could collapse rapidly and irreversibly, at least on human timescales. Others suggest it is more resilient than that the feedback mechanisms are complex enough that the circulation will slow but not stop. We don't know. We genuinely do not know how stable the system is. The ocean circulation that has been regulating the climate of this planet for millions of years, that has made Western Europe temperate, that has distributed heat and nutrients and oxygen across the global ocean, that has been one of the most important physical systems in the habitability of the planet. We cannot predict with confidence what will happen to it. We can model it. We can measure it. We can observe that it appears to have slowed in recent decades. But the behavior of a system this complex, driven by this many interacting variables, in conditions that have no close historical precedent, that remains one of the deep, pressing, unresolved questions of Earth science. The ocean's heartbeat may be changing, and we are not yet sure what that means. Let your body settle deeper. The thought of that circulation, the slow, 1,000-year turning of the ocean's deepest water, carrying its cold and its chemistry and its ancient darkness from ocean to ocean across the span of human civilizations. Let it carry you rather than trouble you. The ocean has been doing this for millions of years. It is a system of extraordinary resilience and complexity, and it is still going right now, in this moment, as you lie still. Somewhere in the North Atlantic, dense cold water is beginning to sink. Somewhere in the deep Pacific, water that last touched the surface 1,000 years ago is slowly rising. The circulation continues. The ocean breathes. There are parts of the ocean where things happen that violate or appear to violate what we expect, not in supernatural ways, not in ways that require the abandonment of physics, but in ways that reveal how much more complex the physical behavior of the ocean is than our models can currently capture. Ways that show us, again and again, that the ocean is not a simple system, not a bathtub that follows straightforward rules, but something layered and dynamic and full of emergent behavior that arises from the interaction of thousands of variables in ways that cannot always be predicted. Internal waves are one of these things. The ocean surface has waves, the ordinary wind-driven waves that every beachgoer knows. Waves that are visible, audible, that you can feel against your legs when you stand in the shallows. But deep within the ocean, where the water is layered by temperature and salinity into strata of different density, there are other waves, enormous, invisible, slow-moving waves that travel along the boundaries between density layers rather than along the surface. Internal waves can be gigantic. Some of the largest internal waves in the ocean, measured by underwater instruments since they are invisible from above, can be hundreds of meters tall, not wide, not surface spanning, but vertically hundreds of meters from trough to crest, surging along the interface between cold, deep water and warmer surface water, like a slow underwater tsunami. They form when tidal forces or other large-scale ocean dynamics push dense water up against lighter water, creating oscillations that then propagate along the density boundary. They travel much more slowly than surface waves, sometimes only centimeters per second. But they transport enormous quantities of energy, mixing water between layers, generating turbulence when they break, and affecting the distribution of nutrients and organisms throughout the water column. They affect submarines. Internal waves have been blamed for incidents in which submarines, navigating through the deep, encountered sudden, unexpected changes in buoyancy, water suddenly denser or lighter than expected, that caused rapid, difficult-to-control changes in depth. The ocean's internal structure is not uniform, and navigating it requires more than surface knowledge. Internal waves are still not fully understood. The exact mechanisms by which they form in specific locations, the way they interact with topography and with each other, the full extent of their effect on ocean mixing and heat distribution. These are active areas of research. We can observe them with certain instruments and satellite sensors. We can model some of their behavior, but the internal wave climate of the deep ocean, the complex three-dimensional picture of all the waves moving through the interior of the sea at any given moment, that remains far beyond our ability to completely characterize. The ocean's surface is not the ocean. The ocean is a volume, a three-dimensional space of extraordinary complexity, layered and moving and internally structured in ways that are not visible from above and are only beginning to be mapped from within. The question of where whales sleep. This is not a scientific mystery in the deep sense. We know how and when cetaceans sleep, broadly. What it is is one of those questions that, when you let it fully land, opens into something unexpectedly profound. Whales must breathe air. They are mammals, fully adapted to an aquatic life, but still breathing from the surface. Their entire biology, their sleek form, their echolocation, their extraordinary diving capacity, is the product of millions of years of adaptation to the sea. And yet, the fundamental mammalian requirement remains: oxygen from the air, surface access, the periodic return to the boundary between two worlds. And they must sleep. All mammals sleep. The need for sleep is so deeply embedded in mammalian biology that even the most extreme adaptations cannot entirely eliminate it. Cetaceans, whales, and dolphins have solved the problem of sleeping in water through a mechanism called unihemispheric sleep. One hemisphere of the brain sleeps while the other remains awake. The sleeping half gets its slow wave rest. The waking half maintains enough consciousness to continue swimming, to monitor the environment, to control breathing at the surface. Then, after a period, the hemispheres switch. The formerly sleeping side wakes. The formerly waking side rests. Dolphins, in particular, have been extensively observed doing this. They continue to swim in slow circles while one side of their brain sleeps. Their eyes tell the story. One eye closed, resting with the sleeping hemisphere. One eye open, connected to the waking hemisphere, watching. Sperm whales have been observed doing something different and somehow more visually striking. They appear to enter a deeper sleep, perhaps involving both hemispheres simultaneously, that requires them to float motionless at or just below the surface, vertically oriented, like enormous, slowly breathing logs adrift on the open ocean. Groups of them, sometimes, floating together in this still vertical posture, barely moving, their skin barely marked by the lapping of small swells. Sleeping whales, the largest animals on Earth, floating in the open ocean, in the dark, suspended. One researcher, on a small boat in the Pacific, encountered a group of sperm whales, sleeping like this, and drifted quietly among them. The animals were so deeply asleep, they did not respond to the boat's presence. The researcher described the experience in terms that go beyond ordinary wildlife encounter, as something closer to the feeling of being in a very large, very old, very quiet space, something like entering a cathedral, something that asked for stillness by its own example. The mystery here is not just biological, it is phenomenological. The question of what it is like, if there is a what it is like, to be a whale sleeping in the open ocean, is one of those questions that science cannot currently answer, because science has not yet found a way to access the subjective experience of another consciousness, particularly one so different from our own. We can observe the behavior. We can measure the brain waves through attached monitors. We can map, in some partial way, the external features of cetacean sleep. But what the whale experiences in those floating, vertical, open ocean hours of sleep, what the world is like from inside that enormous body, in that specific state of rest, in the dark Pacific water, that is genuinely, perhaps permanently, inaccessible. And there is something moving about that inaccessibility, something that reminds you how many kinds of experience exist in the world that you will never know from the inside, how many forms of consciousness, large and small and ancient and strange, are going about their business in the ocean right now, each one a complete world of its own, each one resting or feeding or calling, or swimming through a version of reality that no human mind has ever fully inhabited. The ocean is full of inner lives, alien, distant, beautiful, and entirely their own. Soften again, just a little. Let the image of those sleeping whales stay with you for a moment, floating vertically in a dark water, enormous and still. Rest in their ancient bodies in the way that ancient bodies know how to rest. You are resting too, right now. Your body knows how to do this. It has known for your entire life. All you have to do is allow it. One of the strangest unexplained phenomena in the ocean's physical behavior is the existence of what oceanographers call dead zones. Not dead zones in the ecological sense, though those exist too and are a different kind of mystery and a different kind of concern. These dead zones are a historical phenomenon, first reported by Scandinavian sailors and documented formally in the early 20th century. They are regions of ocean, typically in fjords or coastal waters, with specific stratified conditions, where a ship moving through the water encounters an inexplicable resistance, as though the water has thickened, as though the ocean itself is pushing back. The effect is real and can be severe. Ships that entered these zones would find their engines straining, their progress slowing dramatically, their propulsive power seeming to dissipate into the water without moving them forward at the expected rate. Early accounts describe ship captains mystified, watching their vessels lose speed and become sluggish in calm conditions, with no visible current or obstacle to explain the resistance. The explanation, when it was worked out in the early 20th century by the Norwegian physicist von Walfrid Ekman, was elegant and unexpected. Dead zones form in stratified water where a layer of fresh or brackish water sits on top of denser salt water, separated by a sharp boundary. When a ship moves through this kind of layered water, it generates not just the usual surface waves, but also internal waves at the boundary between the two layers. Waves that are invisible from above, completely hidden, but that carry away enormous amounts of the ship's propulsive energy. The ship creates waves it cannot see, and those waves drain its power. The dead zone effect can completely halt a vessel that would otherwise move freely through open ocean. The bow wave creates an internal wave that matches the ship's speed, and the two become locked in a resonance that is extraordinarily efficient at extracting energy from the ship's propulsion. The sailors who first encountered this did not know about internal waves. They saw only calm water and a struggling ship, and they named the phenomenon for what it felt like: dead water, water that seemed to have taken the life from the vessel. Ekman reproduced the effect in a laboratory with a tank of layered water and a small boat, and published his explanation in 1904. And yet, more than a century later, the full physics of the phenomenon, particularly the details of how the internal wave in the ship interact in real ocean conditions, with the full complexity of actual water stratification in actual ship hulls, is still an active area of computational modeling. The basic mechanism is understood. The detailed behavior across different conditions remains incompletely characterized. The ocean has a way of turning what appears to be simple, a ship moving through water, into something that reveals unexpected depths of complexity. The surface is calm, the water is clear, and yet something invisible is happening at the boundary below, draining away the energy, leaving the ship suspended between motion and stillness in a way that feels almost deliberate, as though the ocean is holding on, as though, in those specific conditions, in that layered water, the sea briefly asserts something like intention, a slowing, a keeping. That is not, of course, what is happening. The physics is physics, indifferent and mechanical, but there is a quality to the experience, described by the sailors who encountered it before they had any explanation. That touches something in the language of experience rather than the language of measurement, the experience of encountering resistance that makes no visible sense, of feeling held back by something you cannot see, of finding that the world is more complex than it appears from the surface. The ocean teaches this lesson in many different ways to anyone who tries to cross it or understand it or map it in full. Always more complex than it appears. Always something happening below the visible surface. The migration of salmon carries one of the ocean's most enduring mysteries. The Pacific salmon, the Chinook, the sockeye, the coho, the pink, hatches in a cold, clear, freshwater stream somewhere in the mountains of the Pacific coast of North America or Asia. It spends the first years of its life there, in the river, feeding and growing. And then something changes, something chemical, something hormonal, something written into the biology of the fish at a level below conscious experience. The salmon undergoes a transformation called smoltification, a profound physiological reorganization that prepares its body to survive in salt water. Its kidneys change, its gills change, the chemistry of its blood changes, and it begins to move downstream, out of the rivers, into the estuaries, and from the estuaries into the open ocean. Some Pacific salmon travel thousands of kilometers into the North Pacific. They join the vast oceanic gyres, the slow circular currents that move around the Pacific basin, and they feed and grow for years in the open ocean, far from any coast, in a featureless expanse of water that contains no landmark, no visible reference point, nothing that a human navigator would recognize as a guide. And then, after years, they return. They turn around in the open Pacific and begin the journey back to the specific river, to the specific tributary, in many species, to within meters of the specific spot where they hatched. An accuracy that exceeds GPS, or rather, an accuracy that is based on something far older than GPS, something written into the fish's biology by millions of years of evolution, selecting for individuals who could find their way home. How do they do it? Partly by the Earth's magnetic field. Pacific salmon can detect magnetic fields with extraordinary sensitivity, and the specific magnetic signature of the Earth's surface varies with position. Different combinations of field intensity and inclination at different locations. The fish may be imprinting a magnetic map during their juvenile river life, and using that map during their ocean migration to navigate back toward the general region of their birth, partly by smell. The olfactory memory of salmon is legendary. As they approach the coast and enter fresh water, they follow chemical cues. The specific mixture of dissolved minerals and organic compounds that characterizes the water of their home river, so distinct in its chemistry that it can be distinguished from adjacent rivers, so remembered from their juvenile years that it draws them back decades later with something that functions like recognition. But the open ocean navigation, the journey across thousands of kilometers of featureless water before any coastline is in sensory range, using magnetic fields, in sun position, and possibly other cues we have not fully characterized, that remains one of the more impressive, unexplained capabilities in the animal kingdom. We know the broad outlines. We know the magnetic field is involved. We know olfaction matters in the final approach. We know solar position may be used as a compass during the migration. But the integration of these cues, how the fish combines multiple sources of information, how it corrects for current drift, how it maintains directional consistency across the weeks or months of open ocean travel. The algorithm, so to speak, that produces this extraordinary navigational accuracy is not fully understood. The salmon is navigating across the Pacific using a system that we can partially describe but cannot yet completely replicate. It is solving a problem that human navigation technology solved only recently, and that required GPS satellites and decades of engineering, by doing something that has been running in its nervous system for millions of years without anyone's assistance. And at the end of the journey, when the salmon has crossed the ocean and found the coast and entered the river and swum against the current for weeks until it reaches the place where it hatched, it spawns, it reproduces, and for most Pacific salmon species, it dies. The body decomposes in the river. The nutrients it absorbed in the ocean, the marine phosphorus and nitrogen, flow into the river ecosystem, into the trees along the river banks, the insects, the birds, the bears, the small organisms in the streambed. The salmon carries the ocean inland. Every year, in every Pacific coastal river where they still run, the salmon bring the chemistry of the deep water into the mountains. They are a biological pump in the truest sense. Living organisms that move material from one ecosystem to another, connecting the ocean to the forest in a cycle that has been running for millions of years. When the salmon are gone from a river, the trees near the river grow more slowly. The stream insects decrease in number. The bears lose a crucial food source. The entire watershed changes in response to the absence of the marine nutrients the salmon would have brought. The salmon is a thread connecting sea to mountain, ocean to forest, deep water to high altitude. Its migration is not just a marvel of biological navigation. It is the mechanism by which the ocean reaches the interior of the continent. There is a sound in the ocean that has no explanation. It is not the bloop. That sound was eventually attributed to ice fracture. This is something else. It was recorded in 1997 and again in subsequent years. And it has a quality that is fundamentally different from anything in the known catalog of natural ocean sounds. Researchers at the National Oceanic and Atmospheric Administration, monitoring the hydrophone arrays in the Pacific, detected an extraordinarily slow sound, a sound whose frequency was so low, so far below human hearing range, that describing it as a sound at all requires qualification. It was more of an infrasound, a vibration in the water at frequencies of around 52 hertz, just barely within the range of what the largest whales produce, but with characteristics that don't match any known whale species. It has been called the 52 hertz whale. Every year, or almost every year, since it was first detected, the sound reappears in the North Pacific. It moves. It migrates in patterns that suggest a living animal. It calls, repeatedly, in sequences that bear the rhythmic quality of biological vocalization rather than geological process. and it is entirely alone. No other sound in the ocean's acoustic record matches it. Whatever is calling at 52, Hertz is using a frequency that nothing else uses. The mystery is not what the sound is. Most researchers believe it is almost certainly a whale, or possibly a hybrid between two whale species, whose calls happen to be pitched at a frequency that matches nothing in the typical repertoire of any known species. What the mystery is what the animal's experience of that uniqueness might be. If this is a whale, it is calling at a frequency that no other whale can hear, or more precisely, at a frequency that may not match the hearing range in which other whales are most sensitive. Blue whale calls are typically in the 10 to 40 Hertz range. Fin whale calls around 20 Hertz. The 52 Hertz calls are high enough that they may simply not be noticed by the whales whose calls they most resemble. A whale calling in the dark of the Pacific that no other whale can hear. That image has entered popular culture in a way that few scientific observations do. It has been called the loneliest animal in the world. Books have been written about it, documentaries produced, songs composed, because it touches something about isolation, about calling into a space where the signal cannot be received, about existing in a form that makes you unintelligible to everyone around you. Researchers have been appropriately cautious about the anthropomorphic interpretation. We don't know that the animal is lonely. We don't know that it is suffering. We don't know that it is even trying to communicate with others in the way that word implies. Whales produce calls for many reasons, and not all of them are social. But the mystery is real. Whatever is making this sound is apparently a living thing, moving through the North Pacific on a seasonal migration route, calling repeatedly in a register that nothing else seems to answer, and no one has ever seen it. Despite decades of monitoring, despite dedicated search efforts, despite the presence of numerous research vessels in the North Pacific over the years, no researcher has ever connected a visual observation to the 52 Hertz signal. The animal remains acoustically real and visually absent, a presence defined entirely by its voice, a life described only by its sound. The ocean keeps it hidden, as it keeps so many things, as it has always kept so many things. Let the image of the 52 Hertz whale drift through your mind very softly, moving through the dark Pacific, calling in a frequency no one else uses, unheard, perhaps, by every other living thing in the ocean. And yet, the call continues. The animal continues. Whatever it is alive in the Pacific right now, migrating, feeding, navigating, persisting, completely indifferent to the human mystery that surrounds it. It is not lonely in any way that requires our concern. It is simply itself, in the ocean, as it has been for all the years we have been listening. There is something in that thought that is unexpectedly comforting. The idea that a thing can be unknown and still be complete, still be fully itself, still be going about the business of its life in the deep water, regardless of whether anyone can understand or explain or even find it. You don't have to be fully understood to be real. You don't have to be fully explained to continue. The color of the deep ocean is something that no living human being has seen, or rather, the absence of color. The particular quality of the dark in the deep sea is not quite like any other darkness in the human experience. It is not the darkness of a room with the curtains drawn, where some ambient light always leaks around edges. It is not the darkness of a cloudy night, where the sky still emits some faint luminosity. It is not even the darkness of a cave, where the geology glows faintly with moisture and reflected light from far away. The darkness of the deep ocean, below 1,000 meters, is the darkness that exists when every photon from the sun has been absorbed or scattered by the water above, when the only light that exists is the light that living organisms make for themselves, when the visual world, the world of things seen by reflected light, simply does not exist. The first human beings to descend into that darkness and return to tell about it were William Beebe and Otis Barton, who descended in a steel sphere called the bathysphere in a series of dives off Bermuda beginning in 1930. They were not scientists in the narrow sense, though Beebe was a naturalist of considerable reputation. They were explorers in the most straightforward meaning of the word, going to a place no human had ever been and describing what they found. Beebe's descriptions of the descent into deep water are some of the most evocative pieces of scientific writing from the 20th century. He described the transition of the water from blue to green to deep blue-black. He described the moment when the last faint daylight faded and the world outside the porthole became absolute dark, punctuated only by the cold flashes of bioluminescent organisms passing by. He described the experience of sitting in a steel sphere, hanging on a thin cable a kilometer below the surface of the Atlantic, as something fundamentally unlike any other human experience. A place of extreme sensory reduction combined with extreme psychological intensity, where the mind fills the darkness with attention. He reported seeing creatures he could not name, things that passed the porthole briefly, lit by their own light, too fast or too unfamiliar to be catalogued in the moment. Some of what he described has never been confirmed, which may mean he was mistaken, or may mean he was seeing things that have never been encountered again in the limited exploration of the deep. The deep ocean is large enough to hide almost anything. The total volume of the habitable deep ocean, the water below 200 meters, is enormous. Exploration by submersible has covered a tiny, almost incomprehensibly small fraction of it. The chance of any given submersible on any given dive encountering a specific unknown organism is vanishingly small, even if that organism exists in significant numbers. There are almost certainly large organisms in the deep ocean that have never been seen. Perhaps nothing that would qualify as sea monster by any dramatic interpretation, but organisms of significant size whose existence we can reasonably infer from indirect evidence, from predation scars on prey animals, from stomach contents of deep-sea predators, from the occasional body that washes ashore or floats to the surface, without ever having directly observed a living individual. The giant squid was in this category for most of human history, known from dead specimens and fragments for centuries, including the famous tentacles found in the stomach of sperm whales, which clearly indicated an animal of enormous size. It was not photographed alive in its natural habitat until 2004, not filmed in the deep until 2012. For decades after marine biologists were certain the animal existed and had a general sense of its biology, the giant squid remained visually unconfirmed in life. It was real and invisible simultaneously. How many other things are real and invisible in the deep right now? We can't know. That is the nature of this particular mystery. The inventory of what we don't know about deep-sea biodiversity is itself unknown. We can estimate, using species discovery curves and extrapolation from sampled regions, that millions of species in the deep ocean have not yet been described. But estimates of unknowns are, by their nature, imprecise. The true answer could be larger or smaller than current estimates. The only way to know would be to look systematically and thoroughly at the whole deep ocean, and that would require more technology and time and resources than have been dedicated to the task in all of human history. The deep is large, we are small, and so it keeps its creatures and its secrets with the quiet confidence of something that knows it has no reason to hurry. There is a mystery in the ocean that exists not in its depths, but in its surface, in the behavior of something so common and so constantly observed that its mystery is easy to overlook. Waves. Not the physics of wave formation. That is reasonably well understood in its basics. Waves are generated by wind transferring energy to the water surface. The size of a wave depends on the wind speed, the duration of the wind, and the fetch, the distance over which the wind has been blowing across open water. These relationships allow reasonable prediction of wave conditions in most circumstances. What is not fully understood is the phenomenon known as rogue waves. A rogue wave, also called a freak wave or an extreme wave, is a wave that is significantly larger than the statistical expectation would predict. In this language of ocean wave science, a wave is considered a rogue wave if its height exceeds twice the significant wave height, the average height of the top third of waves in a given sea state. In practical terms, this means a single wave appearing in conditions where the typical waves are, say, 4 to 6 meters tall, that is suddenly 12 or 15 or 20 meters tall. They can appear without warning, in open ocean, in sea states that would not lead a careful navigator to expect anything of that kind, and they can be wall-like, nearly vertical faces of water, unlike the gradual slopes of ordinary ocean swells, with a deep trough preceding them that seems to pull the bow of a ship downward before the wave arrives. For much of the 20th century, rogue waves were dismissed by oceanographers. The official position, more or less, was that waves of the size described by sailors who encountered them were not physically possible, that the statistics of wave superposition did not allow for waves that large to arise in the conditions described. The sailors who reported them were doubted. The sailors were not wrong. In 1995, the Draupner oil platform in the North Sea recorded a single wave of approximately 26 meters in a sea state, where the significant wave height was around 12 meters. A confirmed rogue wave, measured by instrument on a fixed platform with recording equipment. It happened. It was real. Since then, with satellite and instrument data, rogue waves have been confirmed in every ocean. They are rare, but they happen. They happen often enough that many of the ships that simply disappeared in the 20th century, large vessels, well-found ships, in sea states that should have been survivable, may have been taken by rogue waves, may have encountered that wall of water without warning, taken it bow on or broadside, and been overwhelmed before any distress signal could be sent. The physics of why they form, the exact mechanisms by which ordinary sea states occasionally produce a single wave of extreme height, is still an active area of research. Several mechanisms have been proposed. The constructive interference of multiple wave trains adding together at a single point. The focusing of wave energy by ocean currents, nonlinear wave-wave interactions that allow energy to concentrate in ways that linear theory doesn't predict. The honest answer is that we don't have a single, complete theory of rogue wave formation that accounts for all observed cases. We know they happen. We know they are more common than classical linear wave theory predicted. We don't fully know why. The ocean surface, which seems like the most observed, most studied, most familiar part of the ocean, still produces events that exceed our understanding. The sea remains capable of surprise. The ocean has a smell, a very specific smell. The salt and mineral smell of the sea air that hits you when you approach a coast. A smell that is distinctive enough that most people recognize it immediately and often find it deeply evocative, triggering memories, nostalgia, the particular emotional quality of past beach experiences, past summers, past moments of standing at the edge of the water. For a long time, the source of that smell was attributed to the salt itself, or to seaweed, or to the general chemical composition of marine air. But the primary source of the characteristic coastal ocean smell turns out to be a compound called dimethyl sulfide, a sulfur-containing gas produced by marine phytoplankton. Phytoplankton produce dimethyl sulfoneopropionate, a molecule that helps regulate their internal osmotic pressure, the balance of water and solutes inside the cell relative to the surrounding seawater. When phytoplankton are eaten by zooplankton, or when they die and decompose, this molecule breaks down, releasing dimethyl sulfide into the seawater, which then volatilizes into the atmosphere. The smell of the sea is the smell of something being eaten. The smell of the sea is the chemical signature of the food web in action, of phytoplankton being consumed, of the energy of the sun being transferred up the food chain in tiny molecular increments. But here is where it becomes truly remarkable. Dimethyl sulfide, rising from the ocean into the atmosphere, is thought to play a role in cloud formation. Sulfur compounds provide nuclei around which water vapor can condense into cloud droplets. The dimethyl sulfide from phytoplankton traveling upward into the atmosphere may contribute to the formation of the marine clouds that reflect sunlight back into space and help regulate the ocean's temperature. The phytoplankton may be cooling the ocean they live in by being eaten and decomposing, by releasing a molecule that rises into the air and becomes part of the cloud formation cycle. The phytoplankton may be participating in the regulation of the very climate that makes their existence possible. The feedback loop, phytoplankton to clouds, to temperature to phytoplankton, is one of the more beautiful examples of biological feedback in the Earth system. It was proposed as a hypothesis called the claw hypothesis in 1987, and it remains somewhat controversial. The magnitude of the feedback effect and whether it is strong enough to be considered a significant climate regulation mechanism is still debated, but the basic chemistry is established. The dimethyl sulfide is there. The nucleation effect is there. The smell of the sea carries within it, in each molecule, the trace of a loop that connects the ocean's surface to its atmosphere and back again. The smell of the sea is the smell of the ocean regulating itself, of the living and the physical connected in a cycle too vast to see. but real enough to breathe. The night is deepening around you. The thoughts are becoming slower, less structured. The science is becoming atmosphere. The facts are becoming images. That is exactly how it should be. Let the smell of the ocean drift through your imagination now. Salt, mineral, something faintly organic and ancient. The smell that lives at the edge of every coast, that has been produced by phytoplankton for billions of years, long before any animal had evolved a nose to detect it. You are breathing in imagination, something that is as old as complex life on Earth. Let it soften you. Let it carry you. There are places in the ocean where the water glows, not with bioluminescence exactly, not to point source cold flames of individual organisms flickering in the dark. Something different. Something that has been reported by sailors for centuries, and that, until recently, remained frustratingly anecdotal. Enormous areas of the ocean surface, sometimes hundreds of kilometers across, glowing with a steady, pale, bluish-white light. Not the flashing kind, not the moving kind, just a quiet, persistent, ocean-spanning luminosity that turns the sea into something that looks lit from within. They are called Milky Seas. The first Western scientific account I am aware of comes from sailors in the Indian Ocean, in the waters around the Arabian Peninsula, describing nights when the sea seemed to glow for as far as they could see in every direction. Jules Verne included a Milky Sea in 20,000 leagues. Under the sea, captains' logs from trading vessels in the 18th and 19th centuries describe them repeatedly. For a long time, these accounts were treated with the same skepticism that greeted rogue waves and many other sailor reports, as exaggeration, as optical illusion, as misidentification of phosphorescent plankton or moonlit water, the kind of thing that seemed too large, too strange, too unlike ordinary experience to be taken literally. In 2005, a paper was published in which researchers used satellite data, specifically low-light satellite imagery from military weather satellites, to actually observe a Milky Sea event, a glowing patch of ocean in the Indian Ocean, roughly 10 kilometers across, but part of a larger luminescent region, measured at approximately 15,000 square kilometers, consistent with a historical ship report from the same location and time. 15,000 square kilometers of glowing ocean. The source appears to be bioluminescent bacteria. Specifically, bacteria that, unlike the brief, flashing organisms responsible for typical ocean phosphorescence, produce a steady, continuous light. They are not flashing in response to disturbance. They are simply glowing all the time in vast populations that can, under specific conditions, become dense enough and extensive enough to illuminate an area visible from space. Why they glow continuously is a biological mystery. The most plausible hypothesis involves quorum sensing, the ability of bacteria to detect the density of their own population through chemical signals, and to change their behavior in response to that density. In dense enough populations, the bacteria may switch on their luminescence collectively in response to a chemical threshold that tells them they are in the right conditions for something. What the biological advantage of this continuous glow is for the bacteria is not entirely clear. It may attract organisms that eat the bacteria's food sources. It may attract animals that carry the bacteria to new environments. It may serve a function that has not yet been identified. The Milky Sea may be a form of bacterial communication that operates at a scale visible from space. Bacteria, some of the oldest and simplest organisms on Earth, producing light shows that cover areas larger than many countries, and that glow steadily through the night over ocean patches that are, at that moment, more densely alive with single-celled organisms than almost anywhere on the planet. The ocean continues to surprise. Even the things that seem impossible, that seem too large or too strange to be real, turn out to be real, turn out to be the ocean doing what it has always done, working at scales and in ways that exceed the expectations of the creatures who look at its surface and think they understand it. The deepest mystery of the ocean is perhaps not any specific phenomenon, not the dead water or the 52 Hertz whale or the Milky Seas or the rogue waves. The deepest mystery may be the fact of the ocean itself, that water exists, that it covers this planet, that its particular properties that seem almost specifically designed to support life, though they are the result of physics and chemistry rather than design, make the Earth the world it is. Water is anomalous among molecules. It is one of the most chemically unusual substances in the known universe, and almost every unusual property it has turns out to be critically important for life. Water expands when it freezes, rather than contracting, as most substances do. This means that ice is less dense than liquid water. Ice floats. If ice sank, if water behaved like most substances, then the ocean would freeze from the bottom up. The ice that forms at the surface would sink to the floor, where it would be protected from melting. Over geological time, the deep ocean would become a solid mass of ice. The circulation would stop. The biology would end. But ice floats. The frozen surface insulates the water below it. Life continues under the ice. The ocean, even in the coldest regions of the planet, remains liquid at depth. Water has an extraordinarily high specific heat capacity. It takes more energy to raise the temperature of water than almost any other substance. This means the ocean acts as an enormous heat buffer, absorbing enormous quantities of energy without becoming as hot as a smaller or less heat-capacious ocean would. It moderates the climate. It dampens the extremes. It slows down the changes that would otherwise occur much more rapidly on a planet receiving variable amounts of solar energy. Water is one of the best solvents in nature. Almost everything dissolves in it to some degree. This is why ocean water is salty. Minerals from the land have been dissolving into it for billions of years, accumulating to current concentrations. And this universal dissolving capacity is what makes water such a perfect medium for biochemistry. Every reaction in every cell, in every living thing, happens in a water medium, using the dissolving capacity of water to bring reacting molecules into contact. The ocean exists, and it exists with precisely the properties needed to make complex, diverse, long-lasting life possible. That may be coincidence. It may be the selection effect of finding ourselves in a universe where things happened to work out. It may be something else, the question of why the universe has the physical constants it has, why water behaves the way it does, why chemistry works the way it works, is a question that goes beyond science into philosophy and physics of a very deep kind. But the ocean is here, with all its properties, covering most of this world, doing all of these things, moderating climate, supporting life, cycling chemistry, absorbing carbon, distributing heat, quietly, continuously, for billions of years. The mystery of the ocean, at its deepest, is a mystery of the world itself. Why anything is the way it is, why anything is at all. The thoughts are very quiet now. The science has become distance. The mysteries have become images. The ocean is somewhere beyond the walls of the room, immense and dark and endlessly turning, holding its questions with the patience of something that has never needed them answered, to continue being what it is. You are very close now. Let your breathing become smaller, gentler, just the faintest movement, in and out, warm and slow. The ocean is breathing too, in its way. The waves are moving somewhere on the surface of the world. The currents are turning, vast and cold, impatient. The milky seas may be glowing somewhere in the Indian Ocean tonight, a soft, impossible light spreading across thousands of square kilometers of dark water, seen perhaps only by satellites, perhaps by no one. The 52 Hertz whale is calling in the Pacific, its low, slow voice moving through the deep sound channel, traveling for hundreds of kilometers in a frequency no other ear is shaped quite right to hear. The sleeping sperm whales are floating in their vertical drift somewhere in the deep blue, one eye closed, one eye open, resting their enormous, ancient bodies in the dark sea. The phytoplankton are doing their quiet chemical work in the sunlit surface, producing oxygen, producing dimethyl sulfide, producing the foundation on which everything else rests. And you are here, still, held, drifting toward sleep the way marine snow drifts toward the ocean floor, slowly, without hurry, with complete willingness. The mysteries of the ocean will still be there tomorrow, patient and enormous, as they have been patient and enormous for billions of years. They don't need you to solve them tonight. They don't need you to hold them in your mind. They can rest too, in their way, waiting in the deep water, waiting in the dark, waiting with all the time in the world. Everything can rest now, even the questions, even the wondering. Let the ocean carry you. Let the dark water be warm and soft and full of slowly glowing things. Let the waves at the surface become smaller and quieter, and then almost still. Let the deep be deep, and the dark be dark, and the night be the night that holds everything. You are doing beautifully. You are already drifting. The ocean is out there, vast and patient and full of things it will never need to explain. And you are here, in the warm, in the quiet, going, gone. Sleep well, and good night.